In this video, we're going to do section 5.3, which is the basic properties of the definite integral. And so what I'm going to do here is start by this first property, which is the integral of a constant function. So it says if k is a constant, then the integral from a to b. So remember, a is going to be our lower bound and b is our upper bound, or our lower limit and our upper limit of k dx is equal to k times the quantity b minus a. So here we have find the integral from a equals 4 to b equals 10 of 6dx. So this is just a number, so k is equal to 6. So this definite integral is going to be following the formula. K is 6 times b is 10 and a is 4, so 6 times the quantity 10 minus 4, or 6 times 6 is 36. Alright, so hopefully this all makes sense, but let me give you a short little graphical representation so that you can see it's exactly what we were talking about before. So if I want the integral of 6, now remember, y equals 6 is just a horizontal line, and I want the integral from 4 to 10, 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10. And here is my rectangle here. Yeah, that's not a very good rectangle, but I think that you guys get the point. But I will erase that little, oh, there we go, I erased it all. I was going to erase that little bit for you to make it look a little bit nicer, but in any event, I think that you can tell that this is a width of 6 and this is a height of 6 over here, and then the area of this is 6 times 6, or 36. So that is the same thing that we've been doing. It's just now we're going to use some formulas so that we don't have to use the Riemann sums, or we don't have to draw this out every time to find the definite integral. Alright, so let's move on to the next one. And if it does seem like it's going to be a lot for you to remember all of these formulas, I agree with you. It is quite a lot. Alright, so now the homogeneous property. If f is a function and k is a constant, and the integral from a to b of f of x dx exists, and then the integral from a to b of k times f of x dx exists, and the integral from a to b of k times f of x dx is equal to, now look at what happened. This is just saying you can bring the constant k out in front so that it's k times the integral from a to b of f of x dx. So if I want to know if the integral from 0 to 5 of f of x dx is equal to 10, find the integral from 0 to 5 of 3 times f of x dx. I can bring that 3 out front. So 3 times the integral from 0 to 5 of f of x dx. Then this guy right here, they just told me was 10. So this is 3 times 10, and the whole thing is 30. Alright, so hopefully you didn't think that was too bad. I don't think that these are too bad, because bringing a constant out in front isn't something that we are too unfamiliar with. Alright, so let's move on to the additive property here. I'll bring that up here. So the additive property is just saying that you can add two integrals together. So I will read that to you at some point, but not right now. Because if you look at the linear property, is actually saying that you can add two integrals together, right? But then you can also bring the constants out in front. So this A was brought out in front and this B was brought out in front. So you split this integral up into 2a f of x dx and then b g of x dx, and then you brought the a out in front of the first one and the b out in front of the second one. Right? That's why I really didn't want to read that additive property to you now, because I feel like this is something that you all can figure out. Alright, so if the integral from 2 to 6 of f of x dx is 10, and the integral from 2 to 6 of g of x dx is negative 2. Now, the one thing I want you to realize is that this a is 2 and this b is 6 for both of these. So I'm not going to mix and match the a's and the b's if they're in a single integral like this. But if this a and b over here happen to be different than this a and b over here, of course I could add them. But I just can't combine them into one integral. So, if that didn't make sense, that's okay. We'll do several examples. I think that you can easily get the hang of this. Actually, I know that you all can do this. Alright, now I'm going to evaluate the integral from 2 to 6 of negative 5 g of x plus 3 f of x dx. So I'm going to split this up into two integrals. Integral from 2 to 6 of negative 5 g of x plus integral from 2 to 6. Oh, I did not write dx here. Well, alright. That's sad. I really just... Oh, here it is. I can undo that. Alright, here. Let me go back and write d of x in there. Actually, you know what I realize now, the last time why everything disappeared, I was pressing the delete key and not the erase key. So, here we go. Now, you don't have to write this step right here if you don't want to. That's perfectly fine if you skip this middle step. I just want to show you how I was splitting this up. Now I can bring the negative 5 in front using the homogeneous property and the 3 in front using the homogeneous property. So negative 5 integral from 2 to 6 of g of x dx plus 3 integral from 2 to 6 of f of x dx. And this integral of g of x was negative 2. And the integral of f of x, this one right here, was 10. So we have negative 5 times negative 2 plus 3 times 10 gives us 10 plus 30. So the whole thing is 40. Alright, so hopefully that all makes sense. Right now, again, we're just plugging numbers into formulas to get a sense for how these different properties of the definite integral work. Alright, so if you have any questions, again, please just send me a message and let me know, or bring your question to the next class. But it is hard for me to see you while you're just watching a video. Alright, additivity with respect to the integral. See, this is very strange. That is not what it says. Additivity with respect to the interval of integration. There we go. So suppose that the function f is integrable on a closed bounded interval I, and that a, b, and c are three numbers in the interval I. Then the integral from a to b of f of x dx, the integral from a to b of f of x dx, and the integral from b to c of f of x dx exist, and the integral from a to c of f of x dx is equal to. Now, this is where I was telling you to be very careful about the limits of integration. See how this is an a, but this is a b, so these two are the same, and then this is a different c right here. Alright, so just make sure that you know what numbers are which. So here's an example of this. If the integral from 0 to 5 of f of x dx is equal to 10, and the integral from 5 to 7 of f of x dx is equal to 3, find the integral from 0 to 7 of f of x dx. So I don't know the integral from 0 to 7, but I do know the integral from 0 to 5, and then 5 to 7. And again, if these two numbers are the same, then I can use this additivity with respect to the interval of integration property. So this integral from 0 to 7 of f of x dx will be the integral from 0 to 5 of f of x dx, plus the integral from 5 to 7 of f of x dx. So this first number they gave me was a 10, and the second number they gave me was a 3. So 10 plus 3 is 13. Alright, so hopefully that all made sense, that you can split the integral up based on the additivity property or based on the additivity with respect to the interval of integration property. Now it is time for two special integrals, and I'm sort of lying here because I'm going to give you two more special integrals. So, I mean, theoretically, all integrals are special, but I think the key is that after this section we'll learn some other ways of doing this so that you don't have to remember every single integral, but these are some important ones anyway. So the integral from a to b of x dx is 1/2 integral, here it is, 1/2 b squared minus a squared, and integral of a to b of x squared dx is 1/3 times b cubed minus a cubed. And then, of course, hopefully you can see the pattern. Integral from a to b of x to the third dx will be 1/4 b to the fourth minus a to the fourth, and integral from a to b of x to the fourth dx is 1/5 b to the fifth minus a to the fifth. Alright. So if this is a 4 here, then the pattern was these become 5s. If this was a 3 here, the pattern is these become 4s. And if this is a 2 here, the pattern is these become 3s. So these are two special integrals here. 1, 2, but the pattern continues. So now, let's try to use the basic properties of definite integrals to evaluate each of the following. So here we go. integral from 0 to 8 of the quantity 8 minus x squared dx. So I don't know all of the properties of integrals yet, but I do know that I can multiply out 8 minus x times 8 minus x to get this into a form that I do know the property to use. So if I multiply out 8 minus x times 8 minus x, I get 64 minus 16x plus x squared dx. And then I'm going to split this up into 3 different integrals. Alright, so this is just using the properties that we've been using. Now please try to remember to put your dx's in here because these are differentials, so don't forget that. Now if you remember for this first one over here, I'm going to use the property integral from a to b of k dx is k times b minus a. So that will be 64 times 8 minus 0. And then for the second one, I have minus 16. If I integral from a to b of x dx would be 1/2 times b squared minus a squared. So that's times 1/2 times 8 squared minus 0 squared. And then for this third one, I have x squared here. So integral from a to b of x squared dx is 1/3 b cubed minus a cubed. So this is plus 1/3 times 8 cubed minus 0 cubed. And I really would encourage you to do this on your calculator to make sure that you get this number by hand, but it is 512 over 3. So you can check to make sure that you are getting 512 over 3. Now, let's move on to part B here. Part B is a little bit different because it's an absolute value. So I want you to look at 1 minus the absolute value of x very carefully. And I'm going to break this up, integral from -1 to 1 of 1 dx minus integral from -1 to 1 of absolute value of x dx. So I really just need to look at this absolute value part. So if you remember the definition of absolute value, it's equal to x if x is greater than or equal to 0, and the opposite of x if x is less than 0. So what I can actually do is split this up into the integral from -1 to 0 and from 0 to 1, because 0 is the point where there is a a, a corner in the function. So what I'm actually referring to here is the fact that the derivative to the left and to the right of 0 are not the same because of this sharp corner at x equals 0. Alright, so now from -1 to 0, this is the negative x part, and from 0 to 1, this is the x part. So negative x and x. Now I have to remember to distribute this negative right here. So if I distribute this negative and then this negative, I have integral from -1 to 1 of 1 dx, and this ends up being a plus. Negative times negative positive, negative times negative positive, so plus integral from -1 to 0 of x dx minus integral from 0 to 1 of x dx. Now, notice that these two are not going to cancel out even though they're both x dx, because this is from -1 to 0 and that's from 0 to 1. So now I've used the rules. This is k times b minus a. So this first one is just 1 times 1 minus -1. And then the second one is this right here, 1/2. I thought I wrote the 1/2 here, so let me write the 1/2 there for you. 1/2 times b squared minus a squared. So this will be 1/2 times 0 squared minus -1 squared, and then this will be minus 1/2 times 1 squared minus 0 squared, and then this will all end up being 1. So you can check this on the calculator again. But again, after I get to some point, all I'm really doing is applying this formula 1 to this integral right here, and the formula 2 to this integral and this integral right here, which are the integrals of x dx. Alright, very good. I know that all of you can do this. So now let's move to example C. This one has the integral from 0 to 4 of f of x dx, where f of x is equal to 2x squared for x between 0 and 2 inclusive, and 4x for x between 2 and then 4 inclusive. So only including the 4 because the 2 was included in the first part of the function. So this is a piecewise function. We've seen piecewise functions before. In fact, we just saw one when I broke the absolute value up into the two pieces. Now, let's try this. So we see that I'm going to have to integrate f of x from 0 to 2 differently than from 2 to 4. So here's 0 to 2, and then this is 2 to 4. So from 0 to 2, this is 2x squared, and then dx. And from 2 to 4, this is 4x, then dx. So now I'm going to bring the constants out in front. So it's 2 integral from 0 to 2 of x squared dx, and bring the constant out in front again. So plus 4 integral from 2 to 4 of x dx. Then I'm going to use my two special properties, just like we've been using over and over again. So this is very good that you are hopefully seeing now that these are the same properties being used a lot. So we have 2 times the 1/3 times 2 cubed minus 0 cubed plus 4 times the 1/2 times the 4 squared minus the 2 squared, and that ends up being, well, 2/3 times 8 plus 2 times 12, so 16/3 plus 24, and that ends up being 88/3. Alright, very good. So if you got through this page, I think that it ends up not being as bad as it seemed, but I'm going to tell you about the non-negative property now. So let me move on to the non-negative property. So if f is an integrable function on the closed interval from a to b, and notice that this one is closed because it has the brackets here. And if f of x is greater than or equal to 0 for all values of x in that interval, then the integral from a to b of f of x dx has to be greater than or equal to 0. So that does make sense, because if the function f of x is always greater than 0, then you would have a positive value that you're trying to find that is between the x-axis and the curve. So that's just like the standard area that we've been finding. I don't want you to think that the value of the area and the value of the integral is always equal to the same value, but if f of x is greater than 0, it will be. Because a thing such as a negative area doesn't exist. You can have a negative value of the integral, but a negative area just does not make sense. Okay, so keep that in mind. Use the properties of the definite integral to justify the statement. Integral from 0 to 1 of x to the fourth dx is less than or equal to integral from 0 to 1 of x dx. So if I'm only looking from 0 to 1, then I do know that x to the fourth is less than or equal to x for x between 0 and 1. Alright, so you can substitute some values in and verify for yourself that numbers in that interval from 0 to 1 satisfy that property. Then I'm going to subtract the x so that I get a 0 over here. And then I'm going to multiply by -1. So -1 times x to the fourth minus x less than or equal to 0. That actually switches the sign because I multiplied an inequality by a negative. Now, what I'm going to do is take the integral. So the integral from 0 to 1 of negative x to the fourth plus x dx greater than or equal to 0. I'm going to use the additivity property to split these up. So negative integral from 0 to 1 of x to the fourth dx plus integral 0 to 1 of x dx greater than or equal to 0. Then I'm going to add this to the other side. So I end up with integral from 0 to 1 of x dx is greater than or equal to integral from 0 to 1 of x to the fourth dx. And then if I want to switch these two around, then I have to switch the inequality sign. So if I do that, I end up with exactly what I was trying to prove over here. So that's all you have to do to justify this. So this is sort of like the any other type of theorem that we're trying to prove in this class, like the squeeze theorem or things like that. You're going to try to uh, sort of work your way from the functions all the way down to what your conclusion is going to be. Alright, I won't do a lot with the non-negative property, but I did want you to see this property here. Now, the next two properties, the comparison property and the absolute value property, I definitely won't talk about any further than this, so they're just here for your reference. But I do want to talk about the mean value theorem for integrals. And so you did have the mean value theorem for derivatives. And the mean value theorem for derivatives was in, I'll tell you the section right now. It was in section 3.1. So just to compare for a second, the, where is it? Section 3.1 had the mean value theorem for derivatives. So this said that f prime of c was equal to f of b minus f of a over b minus a. Very good, right? So the mean value theorem for integrals says suppose that f is a continuous function on the interval from a to b. Notice this is a closed interval again. Then there exists a number c in that interval a to b such that f of c times b minus a is equal to the integral from a to b of f of x dx. So if I divide by this right here, I have f of c is equal to the integral from a to b of f of x dx divided by b minus a. So this is a very similar theorem to the mean value theorem for derivatives. So hopefully you can see the similarity, right? So instead of trying to find the value of derivative at c, I'm trying to find the value of the function at c. So it makes sense that I would be using the integral here. So you can see the more in word statement of this theorem right here. In other words, there's a rectangle between the inscribed and circumscribed rectangles. So remember that this is circumscribed, meaning that it is above the curve, and this is inscribed, meaning it's all under the curve. Alright, so that's the inscribed one. Oop. And that is the circumscribed one. Just remember those words. I know that we've talked about them before, but please try to remember them. And then that just means that somewhere, yeah, there is a rectangle that is where this part outside of the curve is actually exactly equal to this part under the curve. Alright, there we go. So now for the average value of a function. So the value of f of c given in the mean value theorem for integrals is called the average value of f on the closed interval a to b. Thus, if f is integrable on a to b, then the average value of f on the interval is 1 over b minus a times the integral from a to b of f of x dx. And that is exactly what I said earlier when I divided this this b minus a on each side. So let's find the value of the function f of x equals x squared on the closed interval 0 to 2 and find a value of c on this interval such that f of c gives the mean value. So here we go. We have a is equal to 0 and b is equal to 2, and we know what f of x is. So f of c will be the integral from 0 to 2 of f of x dx all over 2 minus 0. So f of x was x squared, and that's all over 2. But I know using my rule that this is going to be 1/3 b cubed minus a cubed. So I have in the numerator 1/3 times 2 cubed minus 0 cubed all over 2. So now let's see. Whoop. In f of c, by the way, if you weren't on the same thought train as I was, is c squared. So then let's go over here. C squared is actually 8 over 6. So you'll have to simplify that. I think that you can see that though. 1/3, 2 to the third is 8. And then that's over 2. And then 1 times 8 is 8. 3 times 2 is 6. Take the square root. C is equal to the square root of 8 over 6. And it is plus or minus, but only the positive square root is in the closed interval 0 to 2. So that is our only solution here. Alright, so hopefully the value of the function on the interval is not too hard. But let me try another one for you, and this will be the last page in this section at least. Find the average value of f of x equals 4x cubed minus 3x squared on the closed interval -1 to 1. So the average value is 1 over b minus a, integral from a to b of f of x dx. So this is very similar to what we were just doing. A is -1, b is 2. So I have 1 over 2 minus -1, integral from -1 to 2, and we have f of x, so I'm going to substitute in the 4x cubed minus the 3x squared. Then I'm going to simplify that, so 1 over 2 minus -1 is 1/3. Then I'm going to use the additive property here, so that's 4 integral from -1 to 2 of x cubed dx minus 3 integral from -1 to 2 of x squared dx. And then for this one and this one, I need 2 of my special properties, so try to remember these properties for the rest of your life. I know that it's sometimes hard to remember these when you have so much other stuff in life that you could be remembering. Like, I have to remember to get the cheese and the eggs every day. So that's one thing that I'm responsible for remembering at home. So now, this is 1/3 times 4 times 1/4 times 2 to the 4th minus -1 to the 4th. Please try to be careful on putting the -1 in parentheses so that you don't make a mistake. Minus 3 times 1/3 times 2 to the 3rd minus -1 to the 3rd. And then if you simplify this, you should get 2. So please try to get 2 on your own. Stop and pause or do whatever you have to do to make sure that you have a chance to make sure that you are getting this right. Okay, let's move on to the next example. Evaluate the integral using the following values. I'm trying to make this a little bit smaller, but I guess I keep on making it bigger. The struggle is real. What a time to be alive. So, evaluate the integral using the following values. Yes, we could actually go ahead and do this using rules that we already know, but they tell us some numbers up here to use. So I'm going to try to use this first one right here. So I don't know that integral of 3 dx, but I do know the integral of dx, so I can move the 3 out in front. So 3 integral from 0 to 4 of dx, and I just saw that that was 4, so this is 3 times 4, which is 12. Alright, next one. I'm going to split this one up into 2 integral 0 to 4 of x cubed dx plus 3 integral from 0 to 4 of x dx minus 5 integral 0 to 4 of dx, and then apply the rules. So I see this one right here ended up being 64. So 2 times 64. This one right here ended up being 8, so plus 3 times 8. And this one right over here we already knew was 4, so minus 5 times 4. So that's 128 plus 24 minus 20, that's 132. Now, the last one is the one that is going to be the trickiest, and I kind of wish that I had all of this on the screen all at once. So I'm going to try to keep all of this on the screen and try not to write too small or anything like that so that you can't see this. But this one is the integral from 0 to 4 of x squared plus 9 dx. So it's the integral from 0 to 4 of x squared dx plus the integral from 0 to 4 of 9 dx. Please don't get tricked by this one because I don't know the integral from 0 to 4 of x squared dx. I only know from 0 to 3 and then from 3 to 4. So I can break this up into integral from 0 to 3 of x squared dx plus integral from 0 from 3 to 4 of x squared dx, and then plus integral from 0 to 4 of 9 dx, and then add together the three numbers that I do know, which are the 9 and the 37 over 3, and then the 9 can come out in front, so I get 9 integral from 0 to 4 of dx. So 9 times this guy, which I know is 4 from over here, and this all ends up being 172 over 3. So again, you can check that, but I do think that if you start understanding these rules and how the properties of the definite integral work, this will not end up being too difficult. What a time to be alive. That is the end of section 5.3.